Yep, that's fine.
Fabulous. Okay, so good morning everyone, and today I'm going to spend a little bit of time talking about our ultra-sensitive gas sensing technique that we're developing at MPL called NICE OHMS. It is a technique that combines cavity-enhanced spectroscopy with frequency modulation spectroscopy. So the aim is to explain the origins of these two mechanisms towards the technique and how this gives this so-called noise immune result. And then show how I've been using it to develop a gas sensor for molecular hydrogen chloride detection and some of the things you need to think about when you're developing this type of instrument. So before we get too started, I feel it's an obligatory motivational side of why we're interested in trace gas sensing. I appreciate we've heard a lot about this already, but just to recap, we're primarily interested in the industrial sector towards the detection of airborne molecular contaminants, or AMCs. These consist of a lot of small molecules that are typically byproducts in the laboratory environment in the microelectronics nanofabrication facilities, where trace amounts of these gases can be sufficient to compromise the integrity of the solid-state device that's been developed. So from this point of view, it's obviously very good to have an instrument that is highly selective, so we know what gas we're looking at. It's highly sensitive, so we can get down to trace levels of detection. It's fast, so it enables real-time detection, so corrective action can take place if we do find there are high levels of a particular AMC. It's calibrated, so it has some form of reliability in the measurement that you're taking. For us, the industry requirement for molecular hydrogen chloride is in the level of 1 nanomole per mole, or in the ppb region. So that's been the motivation for the particular instrument that I'm going to be basing this talk around. However, as we've seen today, there are loads of other applications in environmental by measuring different isotope ratios or whatever in an emission stack, or in the medical sector for breath analysis, where the amount of trace gases in the breath can give you an indication of how well certain medicines are being absorbed by the patient. So with that in mind, the talk is split into two halves. The first half being more the description of the NICE OHMS technique itself, and then a little bit about the things we've considered towards the development of our HCl and water NICE OHMS instrument. So why are we interested in NICE OHMS? And the main reason for that is that it is a very sensitive optical technique, one of the most sensitive optical techniques. And this arises from the different components involved that give it this level. So if we think about what is the acronym, well, it stands for noise immune, cavity enhanced, optical heterodyne, molecular spectroscopy, which isn't very helpful on its own. So the key to understanding NICE OHMS is to unpick these different words in the acronym. So let's start with cavity enhanced molecular spectroscopy. So now we're talking about optical cavities or resonators. So we need to understand a little bit of how these resonators work. Ideally, an optical cavity is simply a system where you can trap light inside, so you can do any kind of mirrors. In this case, I'm showing an example of a plano-concave resonator system. These two mirrors will be separated by a known length, and the aim of the game is to get some frequency to resonate inside such that it is reflecting between the two surfaces and building up power. Now, as we know, when you've got a finite length and you're trying to put light and waves inside it, only particular cavity transmissions are allowed. These frequencies are separated by a free spectral range, which is dependent on the spacing between the two mirrors. So what we want is to have a laser frequency that's of a multiple of the free spectral range that it can successfully couple in the optical cavity and resonate. So now we need to understand this term of cavity finesse. The cavity finesse is effectively like a quality factor for a resonator, is giving you an indication of the lifetime or the number of round trips you've got in the cavity. It is defined as the free spectral range divided by the cavity line width, which is the full width half maximum of this Lorentzian shape on the right-hand side. And it can also be related to the reflectivity of the mirrors. Now, in general, all cavity-enhanced spectroscopy techniques capitalize on the number of round trips you have inside the resonator. And for us, our NICE OHMS utilizes a high finesse cavity, so the higher finesse, the more round trips you have. A caveat to that is that if you do use a high finesse cavity, you're also using very narrow cavity line width. So then you have to be a bit more clever with how you feed back a signal to ensure that the frequency you want to resonate is at one of these allowed frequencies at the free spectral range. So what does this mean for cavity-enhanced spectroscopy? So we think of gas sensing with lasers and absorption spectroscopy. We can think of a very simple system. We have light, it goes through your sample of molecules and it hits the detector. We know that IR transitions are dependent upon intramolecular vibrations. So when we have the laser frequency that resonates with your molecules, it will be an absence of light hitting the detector that you measure. We can quantify this using Beer-Lambert's law, where the absorbance of a material is dependent on the number of molecules, its cross-section, and the path length, which is key. As Jeff has already alluded to earlier, we can then take this cross-section is dependent on the intensity profile and the line intensity and some absorption profile, its frequency dependence, that we can then calculate using coefficients from the HiTran database and be able to model some of these features better. Cavity enhancement really comes into the idea of changing your path length into an effective path length. So if we put two mirrors around our measurement area, we then have a lot more round trips, and then we can effectively, for our high finesse cavity, turn a 10 centimeter path length into the order of 10 kilometers, which is obviously quite important for amping your signal. So here's an example of an HCl spectrum. We have plotted some points from HiTran. We're interested in looking in this region over here, predominantly because in this frequency regime, it's very easy to get components like modulators and detectors. We have now scanned through this area and we've modeled different line shapes. So we can find a nice HCl peak over here. A black line corresponds to 1 ppm, a blue to hundreds, and this red line is the water content at 50% room humidity. So this line is at 1742, and from this modelling, we think we can get to 50 parts per billion detection in 1 minute at 50% room humidity, which is hopefully sufficient for the industrial need. So we've built an optical cavity that's been optimized for this wavelength region. And the key point here is that we really need this high finesse to be able to reach to these really low concentrations. So that's the cavity enhanced side of things. Where does this noise immune and this optical heterodyne properties come from? So we're thinking about optical heterodyne and we're thinking of frequency modulation spectroscopy. Unlike maybe traditional IR absorption spectroscopy, where we've only got a single frequency, frequency modulation spectroscopy arises from modulating our carrier frequency with these two sidebands and creating this FM triplet. And initially, if there's no molecules absorbing, you can consider this triplet to be balanced. And the light in the detector, you don't see any change because it all cancels out. Now, instead of one of our sidebands is interacting with an IR transition of a molecule, there'll be an attenuation of light and a phase shift with this light. And under these circumstances, the FM triplet is now imbalanced, and then we can detect a beat at the detector. So if we take this beat signal and demodulate it, we're able to basically remove some of the noise. How did we do that? So if we think about our 1/f pink noise, if we're measuring up in the gigahertz, which is our modulation frequency that we've put in, and then we demodulate this signal, we're able to then remove a lot of low frequency noises that otherwise we wouldn't be able to achieve. So the question is, why do we see this as a noise immune result? And this is because we're now combining the optical cavity locking and laser stability with this frequency modulation technique. So if we think about our optical cavity, we know that only particular frequencies are able to transmit. The key thing that we need to do is that we have our carrier frequency locked and stabilized to one of these light transmissions. And then we also have to ensure that our modulation frequency is in order with free spectral range to ensure that all free frequencies of this FM triplet are able to transmit and be sustained in this optical cavity. Then it's very simple, exactly the same. You have your FM triplet detector, your gas, and then we are able to detect our beat signal and demodulate and achieve our optical heterodyne measurement. To summarize, this optical cavity is through locking all the FM triplet frequencies that we're able to remove laser fluctuation noise because it is the full FM triplet going through this cavity together. And it is for the demodulation or heterodyning processes that we're able to remove the low frequency noise. And this is where this so-called noise immune result comes from. So now that we've got an understanding of the NICE OHMS technique, let's spend a little bit of time discussing the development of our HCl water NICE OHMS instrument. And one of the key things when you're building a gas sensing instrument is actually handling the gas itself. Gas surface interactions are non-trivial, and HCl is a particularly sticky gas. It's also quite corrosive, and we know that water and HCl have quite an intimate chemistry. We're a lot more familiar with hydrochloric acid than we are with molecular hydrogen chloride. So one of the first things that we did is a stability test. Actually, before I go into that, I should just mention that for us, we're working at HCl levels of concentration where it is very, very low. So the corrosivity is not too much of an issue. It is more the stickiness that can be an issue. So in terms of doing a stability test, we did a measurement where we bought an HCl bottle and then we basically just sent the gas into a commercial cavity ring down spectrometer, and then we waited for the system to stabilize. And then we inserted our material with InVar into the line, and we measured how long it would take till we reached stable conditions to measure. And as you can see in this blue line, it takes a while to reach some form of equilibrium conditions between the absorption interaction with your molecules in the surface, but compared to the such that we actually have molecules reaching the light in our detector. But it never really flattens out. However, in terms of a measurement, if we want a 1 minute measurement, we can kind of, it's at a low enough rate that we can actually get a successful measurement within 8 minutes or so. We also did a reproducibility test where we took 2 concentrations and just simply switched between the 2 bottles. And one of the key things here is that we're able to go from the high concentration to the low concentration with reproducibility. It would be a massive problem if you went from a high concentration, switched off the bottle, and then you found that the desorption of the molecules from the surfaces would interfere with your low concentration measurement. However, you can see in both systems that there is actually still this sort of increasing slope, so they haven't quite reached this sort of ideal equilibrium situation to measure. And for this reason, we decided that we needed to minimize the sticking of our surfaces with coatings. And as our collaborators did quite a rigorous study on this that has already been alluded to, we've chosen, based on their results, to coat our whole system with a Silconert 2000 coating that's supposed to prevent molecules from sticking to your surfaces so that our gas actually reaches the measurement area of the detector and is not just sticking to the steel or the InVar of the cavity material. So in building a NICE OHMS cavity, a few things to think about. One of the things we did is we machined a spacer so that we could stick our mirrors to, so we knew exactly what the length of the cavity was, so we have control of the free spectral range. We also had a piezo on one of our mirrors so we could tune this even better. The spacer is inserted inside of some housing, and we can flush gas in this kind of Z shape so that the gas is continuously flowing into the cavity and out. And then we also prop the cavity up on a few rubber balls to make sure that the spacer is decoupled from the housing. And then simply we put on some windows, and then the light would be shone through the optical axis, or the axis of the cavity. So the system is complex, it's quite complicated, and as you can see, hopefully it's a bit clearer that we've got our cavity and the gas being flushed through the system in this sort of Z shape. And what we aim to achieve is to have our 1742 nanometer laser to probe the HCl concentration and an 1854 nanometer laser to probe the water concentration. And I should add that they will not be resonant in the cavity at the same time. We will be switching between the two wavelengths. So we need to ensure that our frequencies are locked. So we do a pound driver Hall technique to lock our carrier frequency to the cavity. And then we do what's called the Duval-Brewer technique that utilizes these set of electronics to play the same trick to lock our NICE OHMs or our free spectral range sidebands to the cavity. To achieve the NICE OHM signal, you'll see this is approximately 1.5 gigahertz. As we sweep our carrier frequency across an IR transition, we also need to modulate our free spectral range, which we use by the piezo, to ensure that this FM triplet is locked all the way through the measurement and achieve our NICE OHMs output. So for further reading, this is our previous NICE OHMs measurement for ammonia that was done a few years ago. Please feel free to look up this paper. And as you can see, a NICE OHM signal looks a bit like this. This one looks maybe a bit more wonky because there are two absorption lines quite close to each other, but effectively we can take the data points and then we're able to model what the signal should look like using a lot of the coefficients from the HyTran database. One of the key things to note is that all these electronics can be fit into like a board that will slot nicely into a 19-inch rack, and the optics at the moment are all fitting on a 60 by 60 centimeter optical breadboard, so it is a fully portable system. So to finish off, I want to just talk about the finer laser considerations. Since we're using such a high finesse cavity, it has a narrow line width in the kilohertz, and we want the lasers we're coupling in to be as narrow as possible and not broadened. So we did some beat measurements on the lasers that we were using, and we assumed that we had two identical lasers, and the assumption is that the half of a half maximum corresponds to one laser. And you can see that we've got our beat measurement on the left, and on the right we can see that there is a bit of instability with this laser, with the beat jittering around and actually broadening and sharpening over time. So we developed some low noise current drivers using a Liebrecht-Hall design that is quite easy to find in the literature. And then we ran the beat measurement again, and we had a visibly improved noise, and even the jitter and the stability of this beat signal was also improved. And then we did the exact same trick with our lasers that were at 1854 to measure water content, and we saw a similar improvement. And the key point here is that that you don't really want to shoot yourself in the foot if you're making this low noise system. Use a low noise current driver so you're not making your job more difficult. So to summarize, I hope I've given you an idea of the NICE OHMS technique and how it combines cavity enhancement with frequency modulation spectroscopy to achieve this noise immune result that is capable of these nanomole per mole detection limits. That it is important to use a low noise current driver to improve your laser performance. And that your material testing is also important, that you want your gas to reach your measurement area and you don't want it sticking to your surfaces. And in our aim at the moment is to demonstrate a portable and fully operational HCl and water NICE OHM system in early 2021. So many thanks for your time and your patience. I want to thank all those people who have contributed either to this project or our past NICE OHMS project. In particular, Nick Allen, who helped us in gas and particle metrology doing the gas sticking measurements, and the instruments group have helped us design our next generation of our NICE OHM electronics. So if you've got any questions, please let me know. If you don't, here's my email address, and feel free to send something offline. Thank you.
Thank you, Nicola, for your talk. I see we have one hand up already. Genoa, would you like to go right ahead?
Yes, thank you. Yeah, I'm Guillaume Genoux from VTT. Thanks for a nice talk. I just have a small question, or maybe you can comment, because in the previous talk, they were also developing HCl measurement with cavity ring down spectroscopy, but addressing a stronger absorption band in the mid-infrared. So I think NICE OHM is maybe a more complicated setup than the cavity ring down spectroscopy. So do you see any advantage of using NICE OHM? Because like you said, you have more this AOM and are more easily available at this shorter wavelengths, but then you need to address a weaker absorption band.
I think in general it's the frequency stability, and we can use a much higher finesse cavity compared to ring down. Off the top of my head would be the answer to that question. And I think from NICE OHMS it's a more complicated system, but because you've got the frequency modulation side of things going on at the same time, you're achieving the noise immune result, and you can get down to much more sensitive levels of detection. And that would be the short answer. But there obviously, you're right, there are nuances between the two, and you need to weigh up what is your application to whether you go for a super complicated system or not.
I guess the ideal would be to have a NICE OHM at 3 in the mid-infrared range.
Yeah, there is a technique called NICE combs or NICE OFCs, which would be NICE OHMs with a frequency comb. And that's something that's particularly exciting to address the mid-IR levels.
All right, thank you.
Is it?
Thomas has a question, if you'd like to go ahead.
Yes. Yeah, thanks for the presentation. It's a bit more of a general question. So where do you see your development going? I mean, first is the miniaturization, but later on, would you be targeting some different applications or maybe higher wavelengths to get to probe those strong transitions? Or
so I guess in general, every gas is different. You've got different requirements for different gases that you want to measure. So if you want ultra sensitivity, some technologies can do that for some gases and not for others. So it really does depend on the application. So in terms for us, that we found that the hydrogen purity measurement, that actually detecting the concentrations of ammonia is a bit challenging for the current techniques, but for other gases not so much. In terms of emission monitoring, if you need to have ultra sensitive technique for maybe a rare isotope, for example, then perhaps NICE OHMS is quite useful. And as you said, for the mid-IR, and I hope alluded to a bit earlier, there's a technique that combines frequency combs with NICE OHMS, where instead of only having one set of sidebands that are separated by a free spectral range that transmit through the cavity, you end up having a comb of frequencies at the free spectral range. So this would be perhaps one avenue you could go down to get into the mid-IR and access. Again, it comes down to the complexity of your system and what your application is, because for sure, for some applications, you don't need that level of sensitivity, but for some there certainly are. So yeah, as you said, we're working on the AMC, and we're thinking about we're working already in some emission measurements, and we are kind of excited in the trace gas breath analysis. You said earlier is a bit. There's so many different gases that it can be quite hard to interpret your spectra. But we hope with NICE OHMS, if you get down to very trace levels, perhaps it might elucidate better.
Yeah, okay, thanks.
I don't see any other hands. Are there any last questions before we take this first break? If anyone sees anyone, feel free to step up. And how long? We're running about 8 minutes behind, which is actually quite excellent. Thomas or Jeff, should we try to start again on time or give everyone an extra 10 minutes?
Maybe extra 10, because we have a long lunch break, and I would give extra time.
Okay, then let's have the next talk, which will be Timo at 11:40. And thank you all for your attention in this session, and thanks to all the speakers.